only everything in physics only happened in one dimension. But we know that that's not true, and we know that for vector quantities that we are going to be needing to take care of more than one dimension occasionally. You had to solve for a problem in your physics textbook that had you look at the impulse in 2 dimensions. And now we're going to take a look at how to calculate momentum when there's more than one dimension. Because conservation of momentum can be applied in 2 or 3 dimensions because momentum is a vector quantity. If momentum is conserved along the x-axis, it can also be conserved along the y-axis as long as there are no net external forces. So let's take a look at a moving object striking a stationary object. We can pretend in this example that these are billiard balls. Here you have object with a mass of A and a momentum of A moving initially toward an object mass B, and that mass B is at rest. When object mass A has a collision with object mass B, it's not a head-on collision, and the result is that the 2 objects move off in different directions. And since they're moving off in different directions, that means that they're moving off at different angles. We could call theta prime A the angle that the object A moves off in after the collision, and we could call theta prime B the angle that object B moves off in a different direction. And even though this is happening in 2 dimensions, we know for sure that the momentum is still conserved. It's just being conserved in more than one direction. Something that should tip you off on the problem solving for momentum in more than one direction is the fact that we've got an axis here. We've got a y-axis and an x-axis. When we solve for momentum in more than one direction, we want to make sure to set our axes because we're going to be solving for the momentum in the x and the y direction. And if there's 3 dimensions, then we'll have an x-axis, a y-axis, and a z-axis. So you want to make sure to set your axes to solve these problems. And one of the tips that I could give you is always set at least one axis to be parallel to your initial momentum. So here our initial momentum is set up along the x-axis. And so that means that initially, as far as momentum is conserved, there's only momentum in the x-axis. So that means that we should get that exact same value conserved in the x-axis after the collision. In the y-axis initially, there's no momentum, so that means that when we're done, there should be no momentum in the y-axis direction. So that means that we're going to be breaking our momentum, or momenta, into x and y components, where instead of writing just momentum, we're going to write the momentum of object A in the x direction and the momentum of object B in the x direction, and that will be equal to the momentum of object A in the x direction after the collision plus the momentum of object B in the x direction after collision. For this situation that we have up here, the momentum of object B in the x direction was 0, so the mass times the velocity of B will equal 0. So for this situation up here, the initial momentum of object A was all in the x direction, so the mass of that object times its initial velocity will be equal to the mass of the object A times the velocity of the object A after the collision, but that velocity is a vector, it's traveling in this direction, so its momentum is also in that direction. We're looking for the x component, which is this component right here, the x component of momentum, and according to our trigonometry, that's going to be cosine of theta A prime. And likewise, in the b direction, hey, look at that. We've got x and y components of momentum for object B. So for finding object B, it'll be mb vb prime cosine theta b prime. And we would be able to solve for that. In the y direction, it'll be the initial momentum of object A plus the initial momentum of object B, and that'll equal, in the y direction, the final momentum of object A in the y direction plus the final momentum of object B in the y direction. Initially, we set all of our momentum in the x direction, so in the y direction, the momentum is 0 for both objects. So that means that the sum of their momenta after the collision in the y direction will also have to be 0. And that means that this quantity and this quantity are going to have to be equal and opposite to one another in magnitude, and that way they will cancel each other out. And that's how your basic problem setup for two dimensions is going to work. And you should be able to do this for up to 3 dimensions. So let's take a look at example 7-11, which is the very problem that we were looking at, 2 billiard balls colliding in 2 dimensions. So if billiard ball A and billiard ball B collide with each other, we'll give billiard ball A an initial velocity of 3 meters per second. And we'll give billiard ball B an initial velocity of 0. It's initially at rest. We're also going to establish that the balls are equal mass. So that means that the mass of billiard ball A is equal to the mass of billiard ball B, and that's going to be equal to m. When they collide, they're both observed to move off at 45-degree angles to the x-axis. Ball X moves 45 degrees above the axis, and ball B moves 45 degrees below the axis. So that means that theta prime A is 45 degrees in the positive direction, and theta prime B is 45 degrees in the negative direction. What is the speed of the two balls after the collision? Well, we've got momentum, and it's going to be conserved, and it's going to be conserved in both the x and the y direction. So just like we had set up before, we set our axis. So y is perpendicular to the initial pathway, and x is parallel to the initial pathway. Here, the final momentas of A and B are going to have to be broken down into vector components. So we'll set up it for the x-axis first. We'll say that the mass of object A times the velocity of object A before the collision is going to be equal to the mass of object A times the velocity of object A after the collision, but we are only looking for the x component of that value. So that means that we're looking for cosine theta prime A. So that's going to be cosine theta prime A. And we're going to add that to the mass of object B times the velocity of object B after the collision times the cosine of theta prime B. And so you'll note that we'll be able to solve this regardless of if these angles are the same or not. But we can, in fact, solve for this. What we are going to do is we're going to replace our masses with the general m term, and we're going to replace cosine 45 and negative cosine 45. So you've got mv is equal to mv A prime cosine of 45 plus mvb prime cosine of negative 45. So we're going to go ahead and solve here for that value in a moment, but first we'll set up for y. In the y direction, remember, we set all of our momentum so that it was along the x-axis. So that means initially there is no momentum along the y-axis. So that means after this collision, we're likewise going to have no momentum on the y-axis. And if you take a look at the vector components, you're going to see that that should be true. You can visually confirm that that up vector and that down vector are going to sum together to be no vector. So you've got mva prime sine of 45 plus mvb prime cosine of negative 45. And so now we've got two unknowns and two equations. The second equation, for both of them, we're going to need to remember this trigonometric value, which is the sine of negative theta is equal to negative sine theta. So for the second equation, we get that mVA sine theta is going to be equal to mVB. Oh, sorry, I put a sine there, a cosine there, sine theta. And here the masses cancel out, and you get that VA prime sine 45 equals VB prime sine 45, and that means that you get negative VB prime equals VA prime. So they do have equal speeds, as we guessed at first. For the y direction, they're equal and opposite speeds. So in the x direction, you're going to get that cancel out your masses, and you get that VA is equal to VA prime cosine theta plus VB prime cosine theta b. So you're going to get that 3 meters per second equals VA prime cosine 45 plus VB prime cosine 45 in the negative direction. And you get that that means that VA is going to be equal to we said that VA and VB are going to be the same value, so you're going to get 2VA prime cosine 45. And as a result of that, you can set it VA equals VB prime equals VA over 2 cosine 45 equals 3 meters per second divided by 2 times the cosine of 45, or 2.1 meters per second. So you can see all you have to do is break down the vector components, do a little bit of substitution, and you can solve for 2 unknown variables. This is going to be your procedure anytime you have to do something in 2 dimensions. For example, the activity we're doing on Friday, where we're going to be looking at a 2-dimensional collision, because I doubt many of you will be able to accomplish head-on collisions. So, when you're solving for momentum and conservation of momentum, you can follow a series of steps that are going to look a lot like the series of steps that you've been solving for all values. So first you're going to have to choose a system. This has been important since we started talking about conservation, because what you choose as a system determines whether you have external forces or not. You're going to break complex systems down into pieces where different conservation laws apply. That's like what we did in our blowgun lab, where first we had to consider a situation where there was an impulse, and then we had to consider a situation where there was free fall due to gravity. Another example of this would be a situation where first momentum is conserved, and then a situation where then mechanical energy is conserved, and that was the ballistic pendulum when we shot a bullet into a pendulum and determined the maximum height. Once you've chosen your system and broken it down into steps that you can apply different physics laws to, you're going to determine if there are significant net external forces. If you set up a system well, you are going to give yourself an opportunity to do conservation laws. You could do conservation laws for momentum as long as the time interval is very short, and you're going to make sure to pay attention to problem boundaries. Remember, if you're breaking it down into 2 sets, that one variable might not be applicable to another set or another step. For example, the time it took the Q-tip to fall to the ground during free fall is not the same time that the force was applied. Once you've figured all that out, you're going to draw a diagram. Make sure you set up an initial and a final for both energy and momentum. You're going to use arrows and labels on those diagrams so that you keep your work nice and organized. Choose your XY coordinate system and set a positive direction and a negative direction. Apply your conservation of momentum or your conservation of energy laws or your conservation of momentum and energy laws. If you have a perfectly elastic collision, you're going to set kinetic energy before and after the collision equal to each other, or you can use the shortcut equation, which says that the velocities for each object will swap if the mass is equal. You'll solve for any unknowns. If you have more than one dimension, or if you have an elastic collision, you might have more than one unknown, and you'll check your work and make sure that you've gotten a reasonable answer.